In this video, we're going to look at the different types of bonds that form between elements, focusing on predicting which type of bond will be present. In other words, at the end of this, you will be able to predict the type of bond that forms between elements based on their electronegativity values. So let's jump in. We're going to review for just a minute what you already know about bonding in chemistry. You learned that there are two main types of bonds. There are ionic and covalent bonds. With an ionic bond, this would occur between something like sodium and chlorine. In this case, what we have is a transfer of electrons. Ionic bonding involves transferring electrons. So this electron moves over here, joins the chlorine, and forms some ions. The chlorine becomes chloride, a negative ion, while the sodium becomes the sodium ion, a positive ion. They're attracted to each other, and we've got an ionic bond. Again, the electron was transferred, and there was a reason for that. Remember that atoms are all following the octet rule that says that elements want 8 valence electrons. The second kind of bond you learned about is called a covalent bond. Remember, co means together, and valent refers to those outermost electrons. So this is a case where the outermost electrons are getting together, or we say the electrons are being shared. Let me show you an example of a covalent bond. A covalent bond might form between two bromine atoms. Recall that bromine is a halogen, so it has 7 valence electrons. In this case, rather than transferring an electron, these two atoms simply share a pair of electrons. We represent that with a single line in between them to show that there's 2 electrons being shared. This is what we call a covalent bond. Recall why these bonds form. In this case, if an electron were transferred, we would not be following the octet rule. One element would end up with 8 valence electrons, but the other would only have 6. So instead, this is a case where atoms share valence electrons. The second thing I'd like to review with you is a concept called electronegativity. This big chemistry term simply means the ability of an atom to pull electrons to itself when bonding. That's an important part of this definition because there's a whole family of elements on the periodic table that don't typically bond. So this gives us a list of elements that looks something like this, with fluorine topping the list at an electronegativity value of 4. Close behind is oxygen, and tied for third we have chlorine and nitrogen, and on down the list we go. Another way to show this list is putting it on a periodic table like this one here, and notice on this table, anything shaded in red has a high electronegativity, while the lighter colors have lower electronegativities. What you notice on this periodic table, first of all, is there's a number of elements who don't have an electronegativity value listed. Those would be our noble gases. Interestingly, xenon does occasionally bond, and so it does have an electronegativity value. Also, you notice that the elements with the highest electronegativity value tend to be up toward the top right-hand corner of the periodic table. That would be fluorine, oxygen, chlorine, nitrogen. I teach my students an easy way to remember the top 4 elements in electronegativity is phone call. Make a phone call, that is fluorine, oxygen, nitrogen, and chlorine. Phone call. Keep this in mind and we'll come back to this table as we need it. So we've been using this word polar when we talk about bonding. Are we talking about bears or something? No, we're not talking about bears. When we say polar, we're talking about something that has opposite ends. You might say our planet is polar. It has a north end and a south end. Or, if you're talking about a battery, you might describe that as polar or having poles. Yeah, batteries are polar. They have a positive pole and a negative pole, right? Well, what we're talking about in chemistry is a similar concept, 2 opposites. In this case, we're talking about a bond or a molecule that has 2 opposites. One side of this bond ends up positive while the other side ends up negative. Keep this in mind as we study the polar covalent bonds. So let's see if we can put all this together. Sometimes you have two atoms that need to share electrons in order to get an octet. Those elements engage in what we call covalent bonds. If the two elements are sharing electrons perfectly, no one is hogging electrons, they both get equal share of the electrons, we say this bond is not polar. There's no charged ends to it. This occurs when both of the atoms have a very similar pull for electrons. In other words, if you were to calculate the difference between their two electronegativities, you would get 0 or something very close to 0. Sometimes, however, these two elements are sharing electrons, but it's not an even share. Someone is hogging the electrons. If you compare the two electronegativities and you end up with a bigger difference, like 0.5 to 1.8, then we describe that bond as a polar covalent bond. Yes, the electrons are shared, but no, they're not shared evenly. This means one of the sides of this bond will become more negative. In the third scenario, the electronegativity value is so different between the elements that there's really not sharing going on. One of the elements has pulled the electron away to itself, and this kind of bond then is called an ionic bond because the electron was transferred. Now let's look at some real examples. Recall that chlorine has 7 valence electrons. And if these two chlorines will share a pair of electrons, they form a single covalent bond. The question is, what kind of bond is that? Is that a polar covalent bond or is it nonpolar? And so what we do is we look up electronegativity values. The electronegativity of chlorine is 3.0, and that 3.0 describes how well each of the atoms pulls electrons. Now, if you look at the difference between those two numbers, obviously it's going to be 0, and thus we have nonpolar covalent bond. That is because both atoms pull the electron the same, and neither one ends up hogging the electron from the other. Now let's look at hydrogen chloride. Hydrogen has 1 valence electron, while chlorine has 7. This also forms a covalent bond as these electrons will be shared. A quick check of the electronegativity values will help us predict what kind of covalent bond this is. Chlorine has an electronegativity value of 3, while hydrogen's electronegativity is 2.1. So if we look at the difference between these two electronegativities, 3.0 minus 2.1 is 0.9. This difference tells us this kind of bond is polar covalent. Somebody's hogging electrons. The element with the higher electronegativity pulls electrons towards itself, and so we use a notation like this, with a little tail on the arrow that looks like a plus sign, to show us that the electrons are being pulled toward the chlorine atom in this bond. We also use a notation that looks like this. This symbol, a Greek symbol, means a partial charge. It's partly negative. Chlorine is not negative. It didn't steal the electron, but it is partially negative, leaving hydrogen to be partially positive. In our third example, we're going to consider what happens when sodium bonds to chlorine. Sodium has its 1 valence electron, while chlorine has 7. Both of these need to do something to meet the octet rule. One way to predict what happens is to look at the difference in their electronegativities. Again, chlorine's electronegativity is 3, while sodium has an electronegativity of 0.9. The difference between these two values is 2.1. That's a pretty big difference. We got someone that's really pulling electrons bonded to someone that doesn't pull electrons well at all. And this creates what we call an ionic bond. It's because the difference between these two electronegativities is 1.9 or higher. So let's look at one more example and we'll see if we can predict the bonding going on here. I've got 1 nitrogen atom with 5 valence electrons, and I've got 3 hydrogen atoms, each with 1 valence electron. So we would consider each of these as a separate bond, but as you can see, they're all going to have the same difference in electronegativities. Let's look that up. Nitrogen's electronegativity is 3.0, hydrogen's electronegativity is 2.1. The difference between these two numbers is 0.9, telling us that this kind of bond would be a polar covalent bond. In other words, we have a polar covalent bond here, electrons being pulled to the nitrogen, another one here, and another polar covalent bond here, creating a molecule that has 3 partial negative charges on the nitrogen, and each hydrogen has a partial positive charge. One final note that you ought to understand is that this electronegativity difference that we're calculating is really more of a guideline. It's a way to predict what kind of bond will form, but it doesn't always work. Some compounds with an electronegativity difference of 1.9 might be considered polar covalent, while other ionic compounds with a difference of 1.9 might be considered ionic. So there's a little bit of overlap in this prediction. I hope that this helps you as you're predicting what kind of bonds form in molecules.